Hello guys, this is 4.8 anti-derivatives. So before we were looking for derivatives, we are given a function and then we are going to find its derivative using differentiation rules. Now we're going to do the reverse. We're going to go in the opposite direction. So let's say I'm given the derivative f prime of x is equal to 8. Then we can do the opposite direction, the anti-derivatives, opposite of finding derivatives, and we'll get the function that is 8x. And then you can add any constant you want, right? Plus c. Right? That is a constant c. Okay, so let's take a look at the anti-derivative rules or the reverse power rule. So let's start by taking a look at an example. Let's say I have the function g is x cubed, right? And then you take the derivative g prime, which is 3x squared. So the derivative has one less power than the function. And then we have the constant, the power of the function being multiplied to the front of the derivative, right? So we can follow this procedure and then go backwards and trying to get to the original function from its derivative. And here is the reverse power rule. The reverse power rule, let's say f prime, the derivative of a function is x to the power of n, then the original function from the derivative, it's x to the power of n plus 1 over the power n plus 1 plus some constant c. All right, and let's take a look at how this works out with an example. Let's say I have f prime of x is equal to x to the fourth power. Then f of x is going to be x to the 4, right? And plus 1, we need to add 1 power because that's opposite of subtracting power, and divided by the new power 5 plus some constant c. All right, and let's simplify this. That's just x to the 5th over 5 plus c. So this is the power rule in reverse, right here, right? Power rule in reverse. Now, one thing we want to be careful of is that in here, in the form, that n cannot be equal to -1, right? If we get n equal to -1, then we get a 0 in the denominator. Now, in fact, if the f prime is x to the power of -1, then we do actually have a separate rule for that. Right? So the reverse power rule applies to power functions with an exponent not equal to -1. All right, let's try another one. We have f prime is 3x squared plus 2x cubed minus 5. All right, so we're going to do the same thing. That's the derivative of f. Then we want the function f. That means I have 3x to the power of 2 plus 1 over the new power. 2 plus 1 is 3 plus 2x to the power of 3, and then again plus 1 over the new power, which is 4, minus, that's 5 times x to the 0th power, right? X to the 0 power is 1, and then we need to add 1 over the new power 1, and then we also need the plus constant at the end, right? Plus c, any constant that you want, right? And let's see, f of x is going to be x to the 3rd power, right? The 3 over 3 is just gives us 1, and then 2 over 4, that would be plus x to the 4th over 2 minus 5x plus c, right? And that's it. All right, here we have another one. F prime is sine x plus minus 3 secant square x. Now we know that the derivative of cosine x is negative sine x. That means the derivative of negative cosine x is sine x. Right? Now we actually have the sine x in here. That means when we find the original function, going backwards to the original function, that sine x actually comes from the derivative of negative cosine, right? So negative cosine x. Now, from the secant square, for the secant square, we want to know where it came from. And we know that the derivative of tangent x is secant square, right? So secant square actually comes from the derivative of tangent, right? So that will be -3 tangent x. Now, if this were a sine square, this part here, if this were sine square, then we wouldn't know what to do. Or if it were like cosecant, then we wouldn't know what to do, right? But in this case, we have sine and secant square, which are pretty easy to find because they just came directly from one of the differentiation rules. One is a derivative of cosine, and the other one is the derivative of tangent. And we also need the plus constant, plus c. All right, so let's stop here and talk a little bit about why do we need the constant plus c, right? Because let's say if I have the original function f of x is x squared plus 1, and then we take the derivative, we get f prime of x is 2x, right? Where the 1 is gone, right? But if you go from f prime of x back to the original function, by doing the reverse power rule, we get f of x is 2 to the times x plus 1 power, and then divide by the new power. But in this case, we just get x squared. Notice that when we apply the antiderivative, or when we try to go backwards, we lost this plus 1 right here, right? So every time we go back from the derivative to the original function, we have to take consideration into that there might be a possible constant in the original function, and we denote that by using the plus c when we are looking for the original function from its derivative. All right, here we have another one. F prime of x is square root of x plus x squared minus 1 over x squared. Now, the square root of x, we can rewrite that in the form of exponent, meaning we can rewrite it as x to the power of 1/2. Now, the last term here, we have 1 over x squared. Now, we don't have to use quotient rule or any sorts of things like that. As long as we can write it in the form of a power function, then we should be fine. All right, so this is what I'm talking about. We can rewrite this as x to the power of 1/2 plus x squared minus, and 1 over x squared, that can be written as x to the power of -2. Now, notice that the exponent is negative, but it's fine, right? It's still going to work as long as the exponent is not -1, like what we were talking about earlier, then we would be fine. All right, so that is the derivative of the function f in the power form. All right, so basically what we can do is we do the same thing. We just take each term and add a power, divide by that new power. So 1/2 plus 1, that's 3/2. So divide by 3/2 plus x squared plus 1, right? Exponent plus 1, divide by the new power, 2 plus 1, which is 3, minus x to the power of -2 plus 1 over the new power. -2 plus 1 is -1, and then add a constant c. All right, so let's go ahead and clear this up a little bit. The first one, I get 2x to the power of 3/2 over 3 plus x to the third power over 3 plus, right, the -1 in the denominator and the negative sign in the front. They give you a plus sign, right? So that will be plus x to the power of -2 plus 1, that's -1, plus c. Okay, and that's it, right? Maybe you can clean this up a little bit. You can rewrite this as 2 times the square root of x to the third power over 3 plus x cubed over 3 plus 1 over x plus c. Okay, and that's it. All right, so an easier way to check this is you want to make sure that your exponent matches with the number that you're dividing by, right? 2 plus 1 divided by 3, -2 plus 1 divided by -1. Okay, you want to make sure that the new exponent matches with the denominator, with the number that you're dividing. All right, so let's do a quick review about radical x form. So we know that square root of x can be written as x to the power of 1/2. The cube root of x is x to the power of 1/3. Right? And if you have any nth root of x, that's equal to x to the power of 1 over n. Now let's say if you have the fourth root of x to the power of cubed, that is x to the power of third, and then to the power of 1/4. Now, by the power rule of exponent, we can multiply the exponents together. We get x to the power of 3/4. Right? And let's try another one. Let's say a square root of x to the 7th. That is x to the 7th to the power of 1/2. Right? The 1/2 again comes from the square root, and then multiply the exponents together. You get x to the power of 7/2. Okay. All right, now let's take a look at the same derivative, and we want to expand this question a little further. Find the function that has the derivative of f prime and goes through the point 4 and 30. That means the original function f, when you evaluate it at 4, the function value gives you 30. And from earlier, we know that f, the original function has the form 2 times x to the power of 3/2 over 3 plus x to the power of 3/3 plus 1/x plus c. Right now, by pointing this function to a specific value, this is what's called the initial condition. Now, this initial condition is going to help us to find the value of c, right? Because that tells us exactly what the function, where the function is. And in this case, it's saying that, okay, the function actually goes to the power of 430. So what we can do is we can plug x equal to 4 and the function equal to 30, and then we can solve for c, right? So this is what we have. We can say y when x is 4, y is 30, right? Therefore, 30 is equal to 2 times 4, right? So x to the power of 3/4, that's 4 to the power of 3/2 over 3 plus x cubed over 3, that's 4 to the third power over 3 plus 1/x, that's 1/4 plus c. Now you'll see that in this equation, the only unknown is the constant c, right? And all we can do is try to solve for this unknown c. Right? Let's go ahead and evaluate this. I get 30 is equal to so square root of 4 is 2 to the power of 3 is 8. So that's 2 times 8 over 3 plus 4 to the third power, that's 64 over 3 plus 1/4 plus c. All right, and what do we have? We have 30 is equal to 16 over 3 plus 64 over 3 plus 1/4 plus c. All right, and let's see. That's 30 equals 80 over 3 plus 1/4 plus c. Now let's add the 80 over 3 and 1/4 together. What do we have? That's 12, right? Times 4, so 320 plus 3 plus c. Right, so I have 30 is equal to 323 over 12 plus c. Right, and to find c, we can just subtract that over. 30 minus 323 over 12 is equal to c. That means c is equal to that's what, 360 minus 323 over 12. That will give you 37 over 12. Right. So c is 37 over 12. That means we can take that and put it back into the original constant of c in the function, right? So we have a specific function that f of x is equal to 2 times x to the power of 3/2 over 3 plus x cubed over 3 plus 1/x plus the c, constant c, which is 37 over 12. And that is a specific function for our question. All right, what if we have a second derivative and we want to get to the original function? So to get to second derivative, you first start with f, you derive it to get f prime, and then you derive it to get f double prime, right? Second derivative. So what we want to do is now we're going to do reverse power rule twice, right? Reverse once and then reverse twice. to get to the original function f, right? Because we are given the second derivative, so we have to go back twice. Now here is what we have. We have two specific points on the original function f. When x is 0, f is equal to 2, and when x is equal to 1, f is equal to 0. Now these two facts, they're going to help us identify the specific function that we're looking at out of infinitely many possible solutions. All right, so let's start with looking for f prime, right? By applying the reverse power rule on f double prime. So I have 2x cubed plus 1 over 4, right? The new power, and the denominator matches, plus 3x to the power of 2 plus 1 over the new power, which is 3, minus 4x, that's x to the power of 1, plus 1 over the new power of 2, plus 5x to the power of 0 plus 1 over the new power, which is 1, and plus a constant c. Now, in this case, I'm going to call c1 because we actually have to apply the reverse power rule twice, right? So when we do it a second time, we will get another constant. So I'm going to call this the first constant that we have in the first step, which is c1. All right, let's clean this up a little bit. And again, you can check that the new power and the denominator matches, right? 2 plus 1 is 3, 1 plus 1 is 2, 0 plus 1 is 1. So my f prime, after cleaning up, I have the 2's are going to divide with the 4, simplify. The 3 simplifies, the 4 and the 2 will give you a 2 and 5 over 1. All right, so let's see what we have. We have x to the power of 4 over 2 plus x to the power of third minus 2x squared plus 5x plus c1, right? And that's going to be your f prime. Now, in order to get f, we have to perform the reverse power rule again on the function, on f prime. All right, so let's do that. Again, to find f. All right, so add the power, x to the power of 4 plus 1, and then I have a 2 in the denominator, but I need to divide by the new power of 5, plus x to the power of 3 plus 1 over the new power of 4, minus 2x to the second power plus 1 over 3, and plus 5x to the power of 1 plus 1 over 2, plus c1 x to the power of 0 plus 1 over 1. And then we also need another constant, that's c2. All right, and let's see. Let's clean this up a little bit. I have x to the power of 5 over 10 plus x to the 4th over 4 minus 2x cubed over 3 plus 5x squared over 2 plus c1x plus c2. Now, in this case, we have two unknowns, right? The c1 and c2, there are two different constants that we have to figure out. And that's why we have two initial conditions, the two facts, the 2 points that are on the function, 0, 2, and 1, 0. All right, so we're going to use those 2 points to help us find out what c1 and c2s are. All right, so first, let's plug in 0, 2. Right, so f of 0 should be equal to that would be 0 over 10 plus 0 over 4 minus 2 times 0 over 3 plus 5 times 0 over 2 plus c1 times 0 plus c2. And that should be equal to 2, right? It tells us that f of 0 is 2. But you're going to see that all of these are actually just 0. 0, 0, 0, 0. That tells us that c2 is actually equal to 2, right? That's good. That's 1 down, right? And another point that we need is 1, 0, right? You're going to check with 1, 0. So f of 1 would be just plugging 1 into x. I have 1 over 10 plus 1 over 4 minus 2/3 plus 5 halves plus c1 times 1, which is 1, plus c2. Now c2 is 2. We found that in the previous step already, and that's equal to 0, right? Because it tells us that when x is equal to 1, y is equal to 0, right? And let's see what we have. Oh, we have a bunch of fractions. Let's find a common denominator. All right, so I have 10, 4, 3, and 2. Right, so let's see. I think the common denominator is going to be 60. All right, so let's try 60. So first one would be 6 over 60 plus 15 over 60, 60, right? Minus 40 over 60 plus times 30, right? Times 30 to get 60, and times 30 in the numerator, I get 150 plus C1 plus 120 over 2. 120 over 60 is equal to 0. All right, so let's see what we have. We have C1 plus a bunch of stuff over 60. That's 6 plus 15 minus 40 plus 150 plus 120, right, is equal to 0. And what is that? That's 21, negative 19. 270 minus 19. That's 251 over 60 is equal to 0. That means C1 is negative 251 over 60. Okay, and that's C1. All right, now we can just take the function that we had, which is this part, f of x, right? That's f of x is equal to that. And then we are just going to replace C1 and C2 with the two values that we found in the previous two steps, right? C2 is 2 and C1 is negative 251 over 60, right? So our function will look like this: x to the 5th over 10 plus x to the 4th over 4 minus 2x cubed over 3 plus 5x squared over 2. C1, that's minus 251 over 60x plus C2, which is 2. All right, and that's your final answer. That's a specific function that has the second derivative as mentioned in the question, and then the two initial points, 0, 2, and 1, 0. All right, let's look at an application question. A car brake with a constant deceleration of should be 16 feet, 16 feet per second square, producing skid marks measuring 200 feet before coming to a stop. 200 feet, that should be one sentence, before coming to a stop. How fast was the car traveling when the brakes were applied? So first, we know that the position function, S of t, right, that's the position. Let's do a quick review. And the velocity function is the derivative of the position function, right, velocity. And then the acceleration function is the derivative of the velocity, which is the second derivative of the position function. Okay, so we want to find out how fast the car was going, right? That means we want to find out exactly when we step on the brake. Now, the only piece of information we have is that the brake provides a constant deceleration of 16 feet per second square. That means the acceleration of the car of the brake actually is negative 16 because it's constant. And that is the acceleration negative 16 feet per second square. Now, to find the velocity, we know that the antiderivative of acceleration is velocity, right? Because to go from velocity to acceleration, we have to apply derivative. Then to go backwards, to go from acceleration back to velocity, we have to perform antiderivative. That means v of t is actually negative 16 t to the power of 0 plus 1 over 1, right? Because when you have a constant, it's a constant multiplied by the variable to the power of 0. So when we need to perform antiderivative, we need to add a power to the variable, right? So in this case, we have t to the first power, and then plus a constant c. So the velocity is negative 16 t plus c. Now, let's say we begin the skid mark at time 0. All right, let's say we call the beginning of the skid as time equal to 0. That's when we start counting. We need to find the time it takes to get to the end of the skid. To the end of the skid, that means the car is stopped. Car is stopped. Now, when the car is stopped, that means the velocity at that time t is equal to 0. Right? So we want to find out how long it takes for the car to stop. So we can just set that 0 equal to velocity, which is negative 16t plus c. And then we can get that t is c over 16. Okay, so that's the time it takes for the car to come to a complete stop. That's c over 16. Now, of course, we don't know what c is yet, but we'll figure that out in a second. All right, now we have the velocity, and we can also use the velocity to find the position function, right? Because the antiderivative of velocity is position. Right, so we can perform the antiderivative again to find the position function using the velocity. Right, so that would be negative 16t to the power of 1 plus 1 over 2 plus ct plus another constant that's called that d. Right, so you can use C1 and C2 like we did in the previous example, or you can use different letters C and D to represent different constants. All right, so let's see. We have negative 8t squared plus ct. Now c, we got it from earlier that c is t is actually equal to c over 16. Right, so I have c times t, which is c over 16. Right, and then d plus d. Plus d. All right, now we have an initial condition. We know that at the beginning of the skid, the position is 0, right? And that's when t is 0. So when t is 0, s of 0, the position is 0. Right, that's at the beginning of the skid. Right, so let's say we have the skid mark like this. Right, and right here, that's when time starts counting, and then that's when we start measuring the position, right? And then we know that at the end, when it comes to a stop, t is equal to c over 16. All right, so we know that when t is equal to 0, position is 0. That means we can find s of 0, which is 0 plus 减到这里，减到这里。Okay, and that's our position function. Let's clean this up a little bit. We get negative 16, negative 8 t squared plus ct plus d. All right, now let's see if we have any initial values that we can work with. So let's say here's the skid mark, right? Skid mark of the tire. At the beginning, when the first moment that the brake is applied, this is when t is equal to 0, and that's when we are going to start measuring the position, the length of the skid, right? So position is going to be 0. So that's actually a value that we have, is that s of 0 is actually equal to 0, and we want to find out where the car comes to a stop. And from earlier, we know that t is actually equal to c over 16. All right, so we can use this value to try to see if we can get any of the constant c or d in here. All right, so s of 0, that's going to be 0 plus d, which is equal to 0. And that tells us that the constant d is actually 0. So we don't have to worry about that just yet, because that's where we're going to start. So the position function, s of t, is equal to negative 8t squared plus ct. All right. Now, another information that we have on the skid is that it makes a skid marks of 200 feet before coming to a stop, right? So that means at the end of the skid mark, this is s equal to 200, right? That's so the car skids for 200 feet before coming to a stop. That means here we have another piece of information, right? S of c over 16 right? That's the time when the car comes to a stop, is equal to 200. And we can plug that in here and try to solve for c, right? So we have s of c over 16, which is equal to -8 times c over 16 quantity square plus c times c over 16, and that should be equal to 200, right? And let's go ahead and solve this part right here. So I have -8 times c squared over 16 squared. That's I just write it as 16 squared first, plus c squared over 16 is equal to 200. All right. And let's see what we have. That's -8 c squared over 256 plus c squared over 16 is equal to 200. Now we can divide the 8 and the 256. That will give us 32 in the denominator, right? So I have -c squared over 32 plus, and if we make the denominator 32, that's 2c squared over 32 is equal to 200. All right, and we can add them together. I get c squared over 32 is 200. That means c squared is 6400, and c is equal to plus or minus 80, right? But in this case, the value of c determines the time t, right? So we can only take the positive one. So we're going to only look at the positive one. C is equal to 80. That means our velocity v of t is equal to -16t plus c. I know that c is 80. That means the velocity is now -16t plus 80, right? We have a specific function for the velocity. And remember that the question was asking us about how fast was the car traveling when the brakes were first applied. So we want to find out the speed when t is equal to 0, right? Therefore, v of 0, right? So let me actually let me write it down. Speed when brakes were first applied can be found by evaluating v of 0, right? The velocity at time 0, and time 0 is where the brakes are first being applied, right? So we can find that by taking t equal to 0 into the function, the velocity function. So -16 times 0 plus 80, that gives you 80, right? 80 feet per second. Now, if you convert that to miles per hour, that's approximately 54.54 miles per hour. Right, so you're driving at 54, about 55 miles per hour, and then you step on the brake, it will skid for about 200 feet, leaving skid marks before coming into a full stop. Okay, now this is one of the more challenging type of problem. Make sure that you can understand this. Feel free to go back into the video and look at this again over and over again, okay, until you understand every aspect of it. All right, and that's it for antiderivative 3.9. That should be 3.9, 4.8. All right, thank you guys very much, and I'll see you soon.